So I want to talk a bit about what happens when you start with a basic integrated fire neuron. And then you couple that with, say, a potential synapse model, and then how you hook this together. So I want to kind of look at a very particular conversation around an integrated fire sort of core basic neuron structure and kind of look at some of the pieces. Now, a lot of this comes from circuits that were originally thought about and taught by Kwabena Boahen while he was at Caltech as a graduate student. We overlapped together, so kind of these sort of things, but these are sort of measurements and data that I have of these same circuits that I have done over my career to look at these questions. But these are some very interesting kinds of questions to see some of these adaptive loops. Now, the first comment would be as well, I have this integrated fire neuron. I would like to see it eventually reach a synapse element. And there might need to be maybe some additional level shifting to actually get upgoing spikes to be downgoing spikes. So an inverter there, I might need some basic transistor to basically, whether I'm going to have a spike or not and have a particular amount of current. But the core of this sort of synaptic element, and this was something that that Kwabena would use at that time, and I think many people have found popular ever since, is to basically say, let me take something that will, an NFET current source, which actually will constrain it to a specific current level effectively. So this digital will basically, if it's a high voltage, will basically turn this off. If it's a low voltage, it'll actually look like a nice current source. And this will go into what is a typical integrator structure that is in the middle of a current mirror. And this has some very interesting dynamics. Obviously, it has a low-pass filter dynamic, so that's not surprising, but it also has some interesting behavior in the nonlinear space as well. Particularly if you have very large inputs, you will see some different properties there. And that's a longer conversation, but a very interesting perspective. It does give you this sort of current integrating onto a capacitor with some sort of leak here. All right, and so what that allows you to do is get some very interesting dynamics there. And what you might imagine if you saw a particular spike, you would then end up seeing, I would get some sort of synaptic sort of result like this. If I increase that V quanta, which makes it a little bit larger spike, which maybe looks like a bigger quanta of things coming across, coming across synaptic cleft, it would look a little bit bigger, and I could see these things go accordingly. Okay. You do notice you get a very characteristic, very sort of sharp, pointy kind of response through these. Classically, PSPs look a bit different. There's definitely a different shape to what's going on, but it certainly gives you at least a starting kind of model, and one, like I said, that is very popular among many in the neuromorphic community working through these kinds of structures. And so you go, okay, so that looks like a perfectly good synapse, and I can integrate many things. So if I'm firing a neuron, that would be great. And if I simply just put an input, just had a straight input here with some firing, no problem. This neuron would then, this thing would just keep integrating up its response, and I could see that. So here's the interesting thing, and this was something that Kwabena spent, kind of looked at this core structure, and a very interesting structure to play with. Is say, well, what would happen if I took what that current would be and I can make a copy of anything out of that current mirror very directly? What would happen if I actually subtracted that current, what's coming out of there, from the original input? In other words, if I can predict the actual spike behavior, if I can predict that current, then maybe it's not interesting, right? Okay, if I can predict it, I don't need to transmit it. I don't need to send that forward. And this sort of ability to do predictive loops is very, very critical for a lot of different things in computation. It is one way that we often would say take an integrated fire neuron, or that we think of as a sigma delta modulator, and make a second order sigma delta modulator. As you kind of build these higher order loops. Well, an interesting thing happens on the way there is that if I actually do that, I build a neuron that actually is rather adaptive. So normally I would expect a firing pattern to give me a uniform frequency for a given input current. Here's what gets interesting. If I actually look at the output voltage for an input current, it'll start off, and then, interesting enough, it starts firing at a fairly fast rate, but then it starts to slow down, because after a while, it's predictable. And we can then kind of see what's going on with this, how the synapses are building it up. And in fact, this actually has a very interesting sort of slowing down behavior, but it does reach a nice steady state. And we start to find this is important, and almost all the way through at different levels of neurons and neuroscience. You have things that basically are looking for changes and adapt to changes and continue to handle changes throughout. And this adaptive neuron structure is a really, really interesting and very important structure that doesn't get used necessarily on a lot of implementations to date. But the concept tends to be very, very important in many, many different places.